All right, hi everybody. Welcome to Math Background for Machine Learning. I'm going to try and keep this stream pretty short because it's coming from my hotel room while I'm traveling, and also because I'm not posting it at the usual time. It's not a required stream, so I'm just going to go through everything. There's not going to be any questions on Piazza because nobody knows I'm streaming now, and so I think I'll be able to keep it pretty short. All right, so we're going to start by talking about multivariate probability densities. So you remember that we looked at discrete and continuous distributions. And for discrete distributions, we had probabilities, and that was fine. For continuous distributions, for continuous random variables, we had, instead of a probability density, which was effectively the derivative of a probability. It was a function that satisfies this equation here, right? So the density is f, and if you integrate it over an interval, you get the probability that the random variable lies in that interval. So for multiple random variables, the story is similar, but I just wanted to go through the story in order to give an idea of what's going on. So in particular, if we have a function with two arguments, f of x, y, such that if you do a double integral, right, over a rectangle, AB cross CD, of the density, you get the probability that the random variable falls in that rectangle. So x is between A and B, and y is between C and D. So this then is called the joint density, right? It's a density of both x and y, so it's like the joint distribution, but it's the joint density. And you can generalize this to 3 variables and to more than that if you want to. And the difference now is that the probability of an event is now, because there are multiple random variables, it's a multiple integral instead of just a single integral the way it was before. And so you can also generalize the cumulative distribution function, right? It's the probability for some cutoff x on little x on the x variable and some cutoff little y on the y variable, that x is going to be less than its cutoff and y is going to be less than its cutoff. And it's, because this is an event, if you integrate the density over this event, you get the cumulative distribution function. And then, of course, the other way is true too. Because of the fundamental theorem of calculus, if you differentiate the CDF with respect to x and then with respect to y, or the other order, right, it shouldn't matter as long as everything is nice, then you get the density, right? So just as before, density is the derivative of probability. So all of these identities that we're used to for probabilities, they hold for densities as well. They look a little bit different, and the difference basically comes from swapping in densities, so you get integrals instead of sums, for example. So in particular, suppose we have a joint density P of x, y, and you get the marginal densities of x and y. So this is Q is the density of x alone, and R is the density of y alone. And then we'll write S for a conditional density, right? We defined all of these a few lectures ago. And so then the sum rule says that if you integrate the joint density over one of the variables, say y in this case, you get the marginal density of the other one. And the chain rule says that you can get a joint density as the product of the marginal of y and the conditional of x given y. Now, I've written a separate letter for each one of these densities, but it's a very common shortcut to say I don't need to assign a separate name to every density and just use, the letter P for all of them. So with that convention, the sum rule becomes that the integral over y of P of x, y is P of x, and the chain rule becomes that P of x, y is equal to P of x given y times P of y. And so these versions look exactly like the discrete versions, except for replacing sums by integrals, but don't get confused because these are densities and not probabilities. Let's see. The most important single identity is probably Bayes' rule. So it looks, again, exactly like it did in the discrete case, except for replacing the probabilities by densities. And so when you're working with these continuous random variables, multiple continuous random variables, a lot of the time you can forget that they're continuous. The same notation applies, and you can do things like conditioning, marginalization, and applying Bayes' rule without worrying about whether they're continuous or discrete. The only time you have to worry is when it comes to, for example, evaluate the probability of an event, in which case the discrete case you would sum, and the continuous case you would integrate. All right, so now that we've defined multivariate densities, it makes sense to go back and talk about information and entropy for continuous random variables. So these are, again, very similar to their discrete counterparts. In some sense, you could pretty much get by just saying, okay, replace sums by integrals in all of the definitions before. But there are a couple of caveats that we'll get to. So the definition of entropy for a continuous random variable is the integral of p log p, negated. The joint entropy is the same for a joint density function. And then the conditional entropy is, again, the expectation over y of the entropy of the conditional distribution over x. So that's what this is equivalent to. The derivation of that was back when we talked about discrete entropy. And then finally, the KL divergence between two distributions is, instead of the sum of log p minus log q, you have the integral of log p minus log q according to the density p of x. So it's basically the expectation according to p of the log p minus log q. Now, the caveat comes when we start to try to interpret continuous entropy in terms of information, right? So in the discrete case, we had that entropy was the amount of information that you would expect to use to transmit a sample of a random variable from Alice to Bob. Now, if Alice knows the value of a continuous random variable, she actually has infinitely many bits of information, right? Because if you specify it to arbitrary precision, you can't send a real number over a wire. So, so obviously entropy in this case doesn't mean, bits required to communicate something. But, and in fact, there's not really a good interpretation in terms of a number of bits for the entropy of a single random variable. What there is an interpretation of entropy in terms of the difference between the information contained in one random variable and the information contained in a different random variable. So the difference, entropy of x minus entropy of y, tells us how many more bits it would take to transmit x than y, supposing that we use the same accuracy for both, and that accuracy is fairly high. So, maybe appealing to the discrete version makes it a little bit easier to understand what's going on. So suppose that we have, x and y are both defined on the unit interval. And we discretize the unit interval into k equal bins, where k is some large number, 1,000,000 or 1,000,000,000. And so the discrete version of x will have some entropy, and that entropy will correspond to a number of bits. Same thing with the discrete version of y. Their entropies will actually be higher the higher k is, typically, because if you measure them to a tighter precision, then you need more bits to transmit it. But that's fine. You measure them both for the same k, and then you take the difference. And then you take the limit as k goes to infinity, and that is the difference in entropies of the original continuous random variables. All right, so basically for continuous random variables, the absolute value of entropy doesn't mean anything. It's more the difference in entropies that you care about. And so, just for purposes of communicating about entropy, we need to set a 0 point, and we set it somewhat arbitrarily. We set the 0 point of continuous entropy to be the uniform distribution on the interval 0, 1. That distribution is defined to have 0 entropy. And then every other distribution, its entropy is given by comparison to that test distribution. So it's how many more bits do you need to use to transmit x compared to a uniform distribution on the unit interval. All right, and so I've got a derivation here of why it makes sense to think of continuous entropy as a difference in number of bits, and why the the equations that we gave have the 0 point at the uniform 0, 1. I don't think I'm going to go through it right now because it's actually easier just to read the derivation. All right, so let's switch to the next set of lecture notes. So this is about making a model, a joint model of multiple random variables. So we talked for the past few lectures about how to model individual random variables, discrete distributions like the categorical or the Poisson, or continuous distributions like normal or Maxent. In order to make things interesting for machine learning, we'd better have more than one random variable, and so we have to model a joint density or a joint distribution, depending on whether it's discrete or continuous. So that means in particular that we have to model interactions among our random variables. So an example of this might be, we get a patient coming into a doctor's office and we measure height, weight, gender, age, the values of some lab tests, right? You could imagine hundreds or thousands of random variables that you could measure. And the measurement for one patient is just the tuple of all of these random variables. And we want to make a model that acknowledges that these variables depend on one another. So for example, if we know somebody's height, we can tell something about their weight or their gender, and vice versa, right? If we know, taller patients are more likely to be male, and male patients are more likely to be taller. Now, there's actually a couple of ways that people commonly use to build these joint models. We're going to talk about one of them here, which is just to collect all of the random variables together into a big vector, right? So here is one patient who has height 190 centimeters, weight 86 kilograms, gender male, age in years 47. And that's an element of some vector space, which we make as the product of all of the vector spaces for the product of all of the ranges of the individual random variables. Actually, it's not, in this case, a vector space because it has the discrete component. In general, it could be a vector space. And then once we have that vector, we make a distribution over that vector. So we make if it's continuous, we make a density. If it's discrete, we make a distribution, a discrete distribution. There are a bunch of ways to make models of vectors, and so we're going to discuss a few of them here. One of them is the Dirichlet distribution. So this is actually a straightforward generalization of the beta distribution that we used for single probabilities. So if you remember, betas modeled a single probability, like the probability that a coin could land as heads. And the way you would use that is that this probability would have two roles. So it would be a sample from a beta distribution, right? So you have beta of alpha beta, and you draw a sample from that distribution, and you call that sample P. And then you use that sample P as the parameter for another distribution, like the Bernoulli, to model a coin flip. All right, so if you have then more than two outcomes, right, more than just heads and tails, you might have a die roll, which is an integer 1 to 6, or a Unicode character, which I don't even know how many of them there are right now, but there are lots of them. So you have these multiple outcomes, let's say k of them, and so then we need k probabilities, one for each outcome, and these probabilities have to be non-negative and sum to 1. And so the range of the Dirichlet distribution is the simplex, where all of the probabilities are positive or non-negative and sum to 1. And you make a distribution over this simplex with k parameters, one for each of the probabilities, and you get this density function, right? So the main part of it is this here, where you take each of the probabilities, raise it to the power of the corresponding parameter, and multiply them all, and then this normalizing constant, which the actual functional form doesn't matter. You can look it up on the web if you want to. But it makes sure that the distribution integrates to 1 over the simplex. And so Dirichlet distributions arise very naturally from inference about categorical distributions. In particular, suppose we start from a uniform prior distribution over the probabilities of a categorical, and we observe some categorical trials, and we see alpha 1 outcomes of 1, alpha 2 outcomes of 2, and so forth. Then the posterior over all of the probabilities will be Dirichlet with parameters equal to the counts that we observe. And so often when we talk about a Dirichlet distribution, we think of the parameters as virtual counts because it's as if we observed that many counts. And unsurprisingly, beta is a special case of Dirichlet. If you have a Dirichlet over 2 outcomes, then each of the components of that Dirichlet sample follow a beta distribution. All right, another good distribution to work with is a multivariate normal. And this is, again, probably the most common distribution that we'll see. It has 2 parameters, a mean vector and a variance matrix, also called a covariance matrix. And the parameters, unsurprisingly, represent the mean and variance. The variance matrix is always positive definite. And it's also common to specify, instead of the variance matrix, the covariance matrix, it's also common to specify the inverse of that matrix instead, which is called the precision. So given these parameters, the Gaussian density looks like this. You don't have to remember it necessarily because it's very easy to look up. But the key things to remember is that inside the exponential, you have a quadratic form where the inverse covariance tells you the matrix of that quadratic form, and then it's x minus mean transpose precision x minus mean. Right? So here is the density for a Gaussian with a given mean and covariance. If you look at this plot, like for example, if you slice it, the contours or the level sets are going to be ellipses, and that's true for all Gaussians. The center of each ellipse depends on the mean vector, and the shape depends on the covariance matrix. And we talked before about how to use singular value decomposition to understand a covariance matrix, and that works here too. The axes of these ellipses, the contours, level sets, are the singular vectors in the SVD, and the lengths of the axes correspond to the standard deviation in each direction, the square roots of the corresponding singular values. For a multivariate Gaussian, if you marginalize it, in other words, you integrate out one of the variables, you get a Gaussian again. And if you condition on one of the variables, you get a Gaussian again. So Gaussian is closed under, in addition to the operations that univariate Gaussian is closed under, which were sum and scalar multiplication, the ones that we talked about. It's also closed under marginalization and conditioning. And so this is really convenient. It's one of the reasons for the popularity of the Gaussian is that essentially every time you do anything to it, it stays a Gaussian distribution. Let's see. So in addition to the properties that make the univariate Gaussian nice, one of the things that people use multivariate Gaussians for all of the time is it's a convenient way to specify interactions among variables. So these interactions are called correlations, and we'll talk about them a lot more later. All right, so the third way that I wanted to mention was to make a Maxent distribution. And so just like with the univariate, discrete, and continuous cases, you can define a multivariate Maxent distribution. It can be mixed, discrete, and continuous. And again, it works almost exactly the same. You define a vector of statistics, we'll call it t. So for example, we might take the first component of our vector, the second component, the first component squared, the second component squared, and the product of the two components. And then we describe our distribution using the mean parameter, t bar, which is the expected value of our vector of statistics. And given t bar, the Maxent distribution is the one that maximizes entropy subject to the constraint that you hit that given mean parameter t bar. And you can also have a minimum relative entropy distribution, which is the one that minimizes KL divergence from a given base distribution p0. Here's an explicit expression for the Maxent or minimum relative entropy distribution. It's the same as in the discrete case. The difference is that to get the normalizing constant, you have to integrate, and it's potentially a multiple integral in this case. So you might, if it's a mixed continuous and discrete, you'd sum out the discrete variables, integrate out the continuous variables, and then you take the log, of course. And just like before, the gradient of g is going to be equal to the mean parameter for the given parameter theta. A good example of a Maxent distribution is the multivariate normal. We get that one by taking the statistics t of x to be all of the monomials up to degree 2. So in the 2D case, this is what you get, right? First degree monomial, first degree monomial, and then 3 different degree 2 monomials. Now, when we get to multiple dimensions for Maxent, computation can get really bad. So this is something that we're not going to really cover in this course, but effectively, the problem is that it becomes intractable to integrate over a high-dimensional space to get the normalizing constant. And future ML courses say a lot about what you should do to get around that problem. But for this course, what we're going to do is we're going to spend more time with the Gaussian because that's a great example, and because computing and working with Maxent distributions is at worst cubic in the number of dimensions, which means, and sometimes much better, which means that it's tractable to work with the normal distributions in a way that many other distributions are not. All right, so that's everything I think I wanted to say. And we will return later with an actual stream from my office again after I get back to Pittsburgh. Thanks.